Okay, for what we have in this last stage of differential equations, okay, we'll be looking at going back to series, and we have just a bit of a segue to what will be the Bessel function. Okay, we have the method of Frobenius, and now setting up what we have within the method of Frobenius, this will be somewhat reminiscent of the characteristic root equation, and this being reference to a second order differential equation where we have the form y double prime plus, and we have p of x over x y prime, and we have plus q of x over x squared y is equal to 0. And we're going to take some initial conditions, so to speak, where we're going to have utilizing the notations p naught and q naught. And we have this algebraic equation where we have r times the quantity of r minus 1 plus p naught times r plus q naught is equal to 0. And where there is a larger root, r1. Now, when we looked at series for the first go around, okay, we had y is equal to the summation as n goes from 0 to infinity of c of n times x to the n. And where there is a larger root from the method of Frobenius, where we had the larger root designated as r1, we're going to multiply this summation by x to the r1. So we're going to have, putting together, we had the y is equal to the summation as n goes from 0 to infinity, c of n times x to the n plus r of 1. And this will be one of the main ingredients to which we will discover Bessel functions of the first kind of order p. And we have what looks like the letter J, this being reference to the Bessel function of the first kind. And we have for the Bessel function of the first kind of order p, we have that of x, and we have is equal to the summation as k goes from 0 to infinity, and we have of negative 1 to the k all over the product of k factorial and k plus p factorial, and we have times x over 2 raised to the 2k plus p degree. And another way that this Bessel function can be expressed is where we have the k plus p factorial can be written in terms of the gamma function, where we have the gamma of k plus p plus 1. And just recalling what we had with the gamma function. Now we had the gamma of n plus 1 is equal to n factorial. So if we had the n was equal to k plus p, you would have like k plus p plus 1, and the gamma of this is going to be equal to k plus p factorial. Now, for what we have in the case of, say, solving for y, we're going to have the method of Frobenius as well as the development of the Bessel function. And we have x squared y double prime plus xy prime plus x squared y is equal to 0. And let's say if we divide this equation by x squared, and so we're going to have in the rewrite, we'll have y double prime, and we're going to have in the development, now we're going to have x over x squared. And if I put this along the lines of the method of Frobenius, okay, now x over x squared is going to be 1 over x. We have y prime. Now x squared divided by itself would go to 1, but I'm going to keep this ratio in the form of where we had the denominator to be at x squared. So we have x squared over x squared times y. Now recall from the method of Frobenius, you have your p of x over x, q of x over x squared. And so for what we have in this layout, okay, notice you have for p of x over x, and now we have just from the development. Okay, so you have your p of x is equal to 1, and we have from the numerator, this is q of x, which is equal to x squared. And for what we have in the development, we're going to have for the p naught, so you have your p naught is going to be equal to p of 0. But notice we have p of x is equal to 1, so p naught is going to be locked in at 1. Now in the case of q naught, you have q naught is equal to q of 0. And we have q of x equal to x squared, so we have q of 0, that's going to be 0 squared, which is going to be at 0. Now, for what we have in the method of Frobenius, again, so you have r times the quantity of r minus 1, and we have plus p naught times r. We have plus q naught is equal to 0. So we have filling in. Now q naught is negligible. So we're going to have r times the quantity of r minus 1. Again, p naught is going to be at 1. So we have plus r is equal to 0. And what's going to happen here is we have r squared. We have minus r plus r is equal to 0. And we're just going to have repeating root. So we have that r1 is equal to 0. So we have in the development, okay, so we have for y itself. Okay, again, we have with the method of Frobenius, we have x to the r of 1. We have times the summation as n goes from 0 to infinity, and we have c of n times x to the n. And again, since r1 is 0, well, we just have that y, and we have equal to the summation as n goes from 0 to infinity. And we have c of n times x to the n. All right. Okay, so we have, in the case of taking what we have in the development, okay, so we have from the initial stage, okay, so we got that y is equal to the summation, again, as n goes from 0 to infinity. We have c of n times x to the n. Now, we're looking at involving both the first and the second order derivatives. Okay, so we have, in this particular case, right, so we have y prime is equal to, again, we have as n goes from 0 to infinity. Now we're going to have n times c of n, and you have times x raised to the n minus 1. And for what we have in the case of the second order derivative, okay, so you have as n goes from 0 to infinity. All right, so we have what's going to be n times the quantity of n minus 1. We have times c of n. We have times x raised to the n minus 2. And now, we have just in this layout, let me just give you the expanded form case. So we have c naught plus c1x plus c2x squared. And we have, starting from 0, now we have 0, that's going to be negligible, and you have 1 times c of 1, so you have c1, we have plus, it's going to be 2c2 of x, and you have plus 3 c of 3 of x squared, and so on. And if you notice, okay, we have for the second order derivative, okay, so we have 0, 1 makes the term negligible, so if I go out to 2, okay, so we're going to have, so we have 2 times 2 minus 1, okay, so we have 2c2, you have 3 times 2, which will be 6, and so we have 6c3 of x, and so on. Okay, and if you notice, okay, we have, okay, for y prime, okay, since we're starting out at c1, I'll just mention you see we have as n goes from 1 to infinity. We have c of n times x to the n minus 1. And likewise, since we're starting out at 2, this can also be expressed as we have as n goes from 2 to infinity. We have n times the quantity of n minus 1 times c of n times x to the n minus 2. All right, and now in looking at what we have going back to the original equation, okay, so for what we have in the mix, okay, we have among the terms, okay, so you have x squared times y double prime, and so we can say that for what we have in the mix, okay, so you have 2c2x squared plus 6c3x cubed and we have 12c4 x to the fourth, 20c5x to the fifth, and so on. And we have for x times y prime. Okay, so we can say that we have in the mix, okay, so you have c1x plus 2c2x squared plus 3c3x cubed. And for x squared times y, so you have c naught x squared plus c1 x cubed plus c2 x to the fourth, and we have is equal to 0.